Welcome to Math 106, Chapter 1.8, where we talk about derivatives as a rate of change. So recall that from a slope of a line or the constant rate of change has the equation m is equal to y2 minus y1 all over x2 minus x1, given that you have 2 points x1, y1, and x2, y2. Similarly, the average rate of change or the slope of any curve has this particular equation, f of b minus f of a all over b minus a. Now, these values here, a and b, are still given by the points here. So notice how similar these are, right? These two equations are very similar. They've just wanted to distinguish the difference between a constant and an average, right? Constant rate of change, it's not changing. An average, it is changing. So therefore, if we're looking at your average rate of change, they're just taking b here, right? Your x value of b, and then they're doing f of b, which is your y coordinate. So f of b here, f of b here. Then we're going to, again, do a, which is, again, the x coordinate, and then f of a. Very similar to these here, which if I were to highlight their corresponding ones, notice that they are very, very similar, right? They are working together. Now, before we were talking about the constant rate of change, we just went ahead and labeled x1, y1, x2, y2, right? Because it didn't really matter which went first. The same rule applies here. Order doesn't quite matter as much, but they want to be a little bit more hesitant with that. Think about b, because we want to stick with this formula. Think about b as being the bigger number. We don't care if your y is bigger. You may want the bigger of the two x values to come first. Therefore, its corresponding y value should come first. So b, think bigger, and then it'll conform into this equation. So when it says example 1, if f of x is equal to x squared, calculate the average rate of change of x over the rate over the following intervals between 1 and 2. These are your x values, right? So these are x values. Now, which x value is the bigger of the two? That would be this one. So number 2 is b, and number 1 is a. Now, because we can, so far we have your a and your b listed, how do we go about finding your f of b and your f of a? Well, we just listed what b is, so now we need to find your counterpart. We have, right now, the coordinate 2 and I don't know its y, or 1 and I'm not sure of its y. So what we need to do is go ahead and plug in to its formula, into its function, a 2. And same thing here, a 1. We need to go ahead and find the y. Find the y. So if we know b is really equal to, when x is 2, we can take your formula, f of x, and evaluate it at 2. So instead of having x squared, we're going to have 2 squared. So at 2 squared, we're equal to 4. So we now have the coordinate 2, 4. We'll do it again with a. When a, we said, is x of 1. So we're going to do the same thing and evaluate when x is at 1. So 1 squared is just itself. So 1, 1. This is b and f of b. This is a and f of a. So let's go ahead and put it into your formula, which previously we just saw the formula is f of b minus f of a all over b minus a. Our f of b here, which I want to keep with the same colors, our f of b is 4. Our f of a And I chose the wrong color, of course. There we go. Your f of a came out to be 1. So in your numerator, we have 4 minus 1. In your denominator, we have b, which we said established was your 2. So we have 2 minus, and your a is 1 here. So 2 minus 1. Therefore, the average rate of change, so your slope is changing on this parabola between 1 and 2 for an average of 3. So your slope on average is about 3. So we can see that as well if we're looking at, again, taking your parabola, this being f of x is equal to x squared here. And what we've done is we're now finding a line, right, that is running through the point 1, 1 and 2, 4. That is exactly what we found here, right? 1, 1 and 2, 4. So we've cut this thing. This is now no longer the tangent line because it's not touching your graph once, but instead it's touching it twice. This is the secant line. And if we were to zoom into this form, we'll see it right here, again, where we have 1 and 1, and again at 2 and 4. And we could find your slope here by going 1, 2, or sorry, they're actually not going in full. So we went from 1 to 2, so this is 1, and we're going up by 1s. So we'll go up 3 and over 1, given that this is 4, 3, 2, 1, and 0. So you can see that your average rate of change between these 2 points is about 3. Now, the average rate of change between these 2 points particularly is considered the secant line. This is also referred to as the difference quotient. Your difference quotient is a variation of this, but in just more of different variables, because the average rate of change, your difference quotient has just a different, the same equation, just using different variables, pretty much. It just is the derivative described as the instantaneous, there we go, instantaneous rate of change at that value. So your difference quotient, looking at your denominator, right? Looking at the run, we're taking the difference between A and taking A and adding a value to it to get to the next portion. And then your difference in height, we're taking, right, this height here, which again, if we started at f of a and we now added something onto it, this is taking the y value of the additional added value. So this is your slope here. This slope is the average rate of change, also known as the difference quotient. So when it says, what is the average rate of change over the interval of 5 to 6? So 5 to 6. Oops. Let's go ahead and find your average rate of change. So first off, do we have full coordinates? No. So step 1, we need to find your coordinates. In our case, what is B? Well, B is 6. It's your bigger of your 2 values. So let's go ahead and find your coordinate. And I'll push this down. So step 1, find the coordinates. So find f of B. So we take your equation and substitute in a 6. So we have 6 squared plus 3 times 6 minus 5. So we have 36 plus 18 minus 5. So we have 49. So we now have the point 6, 49. So this is B and f of b. Now we need to do the same, but now let's find f of a, where a is the smaller of the two values. In our case, it's 5. So now we're looking at 5 squared plus 3 times 5 minus 5. So we got 25 plus 15 minus 5, which is equal to 35. So now we have a and f of a, which is 5 and 35. So now let's go ahead and find your average rate of change. I like to abbreviate average rate of change as AR and then your little delta symbol change. So it says f of b minus f of a all over b minus a. Therefore, f of b we said was 49 minus f of a we said was 35 all over 6 minus 5. In your numerator, we have 14 all over 1. So we have 14. And your average rate of change can be negative based on just if your graph slope is increasing or decreasing. So don't freak out if you do come up with a negative value. It is perfectly fine. Now, when it moves on to B, when it says what is the instantaneous rate of change, this is looking for the actual rate of change at that particular point when x in our case is equal to 5. So this is just looking for the tangent line, the slope of the tangent line. So in our case, right, we want to take the derivative of your function. So our function was, and it's in t. We have t squared plus 3t minus 5. So if we're looking for the slope of the tangent line when t is equal to 5, let's go ahead and take your first derivative. Let's see if you can pause here and kind of take it over. So we should get 2t plus 3. So now let's evaluate when t is equal to 5. So we can go ahead and say, okay, well, f prime of 5 is equal to 2 times 5 plus 3. So we get 13 here. So at that particular instance, your slope of your tangent line, I don't know if it gave us any concept. No, the slope here is at 13. So if I were to draw a quick picture here, I'll even take that out. So let's say this is t at 5. Your slope here, I don't know if I did that correctly. There we go. Your slope here is at 13. Whereas the difference in this one, we're actually looking at the slope between 2 points at 5 and 6. There we go. This is on average 14. Now, when it comes to real world, and actually one more thing to emphasize before I move on, I want to assume it's asking for instantaneous unless it specifies for average rate of change. So assume that it's instantaneous. We want the slope of the tangent line unless it asks specifically for the average rate of change. Now let's get into some real world context in which we could see, okay, well, what is the difference? What is the usefulness? So picture yourself driving your car on any given day, the car's speedometer tells us how fast we are moving. That is, how fast our position, and they like to use S of t, is changing over an instant. So if the car is traveling at a constant speed over a period of time, you turn on your cruise control, or perhaps you turn on your cruise control. Then the speedometer reading, your instantaneous velocity, is equal to your average velocity. So if, in definition, S of t denotes the position function, so where you are, of an object that's moving in a straight line, then the velocity of the object is given by the velocity given its position, right, is distance over time, right? That's how you get your velocity typically. But you're taking that position over, like that distance, the position over that specific time, and that's going to give you your velocity. Your velocity is the first derivative of your position. So then, right, we go from position to velocity, and now let's figure out what is the next step. So if we then take the derivative of velocity, what would we get? Well, we would get your acceleration. So it goes from position to velocity, your speed, to then how fast did you accelerate your car? So where is your car? How fast is it going? And then how much did you speed up or not at all, right? Decrease. So therefore, if we're taking into account your acceleration is the first derivative of your velocity. Or in terms of your position, it is the second derivative of your positional function. Second or first derivative of velocity. So now let's put it to action. When it says a ball is thrown straight up into the air, its position may be measured as the vertical distance from the ground. Let S of t be the height of the ball in feet after t seconds, S of t, which is equal to negative 16 t squared plus, oh, actually, this isn't the car problem. Oh, no, this is fine. This is just another take. Sorry, I thought we were doing the car problem first. We're just talking about a ball first. So we have a ball that's being thrown up into the air. And we want to find the displacement of the ball given this formula over the interval, over the x values of 0 and 2. So when it says the displacement, what does that necessarily mean? Right? Displacement is the change in your height. Well, the change in height, right? That is just your change in your y values. So you're given x values. Your first thing is to figure out how much is your y value changing. So let's say this is my function here. There we go. If I go from 0 to, let's say 2 seconds is over here, right? I'm starting at some position for x, and I want to know my displacement. I end up at this height, and I want to know by how much did my height change. So I'm looking for this distance right here, this displacement. So first, let's find f of 2. Or in our case, it should be s, since that's the variable that you're using. So it says negative 16 times 2 squared plus 64 times 2. So we should get negative 16 times 4 plus 128, which is equal to negative 64 plus 128, which is equal to 64. So at 2 seconds, we are now at 64 feet. So this is equal to 64 feet. And if we did the same, but for 0, s of 0, it's much easier to calculate, given that we have taken off from the ground, we're at 0. So your displacement, right, your change in height is just going from your 64 feet all the way back to 0. So we have a change of 64 feet. If it was something different, if we weren't starting at 0 and perhaps at 1, right, we would find the distance, your height at 1, and then we again subtract the 2. Now let's find the average velocity. Let me make that a little bit more. Average velocity of the ball during the interval of 0 to 2. So when it's talking about the average, right, we're talking about the average rate of change. That is what your velocity is. So let's figure out your average rate of change. This says f of b minus f of a all over b minus a. Now, thankfully, we have f of b and f of a from your previous step. So f of b we said was 64 minus f of a was 0 all over b 2 minus 0. So we're really working with 62 or 64 divided by 2, which is 32 feet per second. So on average, right, we're moving at about 32 feet per second over the course of these 2 seconds. And it's going to be positive because we're going up. And you'll notice that there is that relationship, that displacement here. So in your numerator, that is that displacement. Of your height, right? Your distance over your time, and this is the difference between your time. That's how you get your average rate of change. Now, when it says what is the velocity of the ball after 1 second, and then 1.5 seconds, and 2.5 seconds, and then let's evaluate what is happening. So it says, what is the velocity at the ball for that one? So is it asking for an average or an instant? Well, because it's at specifically 1 second, this is going to be looking for an instantaneous rate. And again, instantaneous rate of change, right? Change, we're looking for that first derivative. We are given a formula, right? F of our S of t is equal to negative 16 t squared plus 64 t, I believe. Yep. And we want to know at 1 second or after 1 second, what is your velocity? So first thing we need to figure out is, what is the velocity equation? Well, velocity is your first derivative of s, or of your position. So v of t is equal to negative 32 t plus 64. Now we're evaluating specifically, now that we have your slope equation, right, your velocity, we now want to evaluate when t is equal to 1. So v of 1 is equal to negative 32 times 1 plus 64. So negative 32 plus 64 at 1 second, right? We're now at 32 feet per second. If we did it again, when t is at 1.5, do it again. What are we going to see when it comes to your velocity? Can you give it a guess? So we should get 16. So now that's 16 feet per second, and these are feet per second, feet per second. Why is it less even though your time is getting bigger? Well, when you think about what this is going to look like, right? This is a ball being launched, right? Initially, it had so much force behind it that you're launching up rather quickly. But as time continues, what do you see about that velocity? Right? Well, it starts off really quick. We're gunning it. Then it starts to slow down until it stops altogether. And then we continue to then get faster and faster, but we're going in that downward motion, right? But we're still going rather quickly. And I missed my 1.5 here. So what would we expect at 2 seconds? Are we going to be faster or slower than a time of 1 or a time of 1.5? Well, when t is equal to 2, let's go ahead and figure that out. Negative 32 is equal to negative 64 plus 64. It's equal to 0. Is that possible? Yeah, where are we on our graph when your slope is equal to 0 of your tangent line? Your tangent line is right here. So at the top, at 2, your slope is equal to 0, and you have a height of 64 feet. And that, my graph is probably a little wrong over here. I should probably move my 2 over ever so slightly because it's now at my vertex. Right? The height, max height for me is at 64 feet. So we said, what's happening? Well, for this duration from 1 second to 1.5 to 2 seconds, your ball is slowing down. We're starting to reach the peak of your graph. So it's starting to slow down. And in the future, we're going to be, this is just graphing your positional function. We're going to be graphing your slope. Notice that your slope starts out really big, and then we're starting to decrease over time, and then we get down to 0. And then we get into a negative slope. So now it says, what is the acceleration after 1 second and 1.5 seconds? So how do you find acceleration? Well, we take your velocity, which, keep in mind, your velocity is just the first derivative of your positional function. And to get to your acceleration, which is the second derivative of that positional function, and derive. We're just at negative 32. So even if we have at time of 1, we're still going to be at negative 32 feet per second. And why is it negative? Well, after the initial launch, right, all of these factors are coming in play that your acceleration, we should start to decrease over time. At 1.5 seconds, you're still at 32 feet per second. So let's finish these out. At what time is the velocity negative 32 feet per second? The negative sign indicates what about your ball's position? Well, the negative sign indicates that the ball's height is decreasing. Not so much that you have a negative speed, it's just that your height is falling. Right? Your height here, your slope is falling because your height is falling. So if we know v of t is equal to negative 32, we also have your equation for your velocity, negative 32, t plus 64. What are we going to do like we've done in previous sections? Well, these are both equal to one another, so we can set these also equal to one another. Negative 32 feet per second is equal to negative 32 t plus 64. Solve for t, get t alone. Maybe you subtract 64 to the other side. Then you get negative 96 is equal to negative 32t. Divide by that negative 32. So now we get t is equal to 3 seconds. So at 3 seconds, we should be at negative 32. And we can do this given any sort of velocity that we're curious about at a specific value. We can find at what time did that get achieved. Now, at times we might not have, we may not have achieved a specific velocity that we're curious about, in which case your answer wouldn't necessarily make sense. So it says, when is the ball at the height of 48 feet? Well, keep in mind what we know so far about your graph, right? If this is your graph here, we said at 2 seconds, we're at 64 feet here, and that's 0. So 48 feet, let's say this is about 48 feet here. How many different solutions can we achieve at 48 feet? We should have 2 solutions at 48 feet, right? We need to figure out what those solutions are. So for us, if we know that, and again, it being a height, so we're looking at your positional graph one more time. So we have negative 16 t squared plus 64. So we're looking at our 64t. We want to know when your position is at 48 feet. Again, those being equal quantities, we can set them equal to one another and solve. Now we have a negative 16 t squared, so us having a negative leading coefficient for a square. Let's go ahead and bring things to the other side to make it positive. So we should get 16t squared minus 64t plus 48 is equal to 0. Now, what do 16, 46, and 64 and 48 have in common? Well, they all have a 16 in common, so we can factor that out. Now we can go ahead and factor if we'd like. Let's see, factors of 3, so that's negative 3 and a negative 1. Set them both equal to 0. You can ignore the 16 because there's no, we didn't take out a t, a variable with it. So even if we did, 16 is equal to 0, that doesn't make any sense. So at t is 1 and t is 3, we're at 48 feet. We also know that your acceleration at that, your velocity there is at 32. So that's great. Let's see, what other things can we add? We have, again, another 32 here. So this one, your velocity is at 32. Your velocity here is at 0. So that is pretty good. Let's see. Your acceleration as well is at 32. All right. So now last thing, when will the ball hit the ground? At what velocity will it hit with? So with us having the ball hit the ground here, right? Oh, not here. We started at the ground and we stop at the ground. We want to know how did this happen, right? Well, with it, and there's a couple different ways we can approach this. We can either go ahead and try to factor and solve, or we can think about symmetry, right? This being a very symmetrical graph, right? It took 2 seconds from the start of your graph all the way to get to the max height, meaning that it's also going to take that 2 seconds to apply to also achieve the ground. So we should be seeing us hitting the ground at 4. Now let's see the math behind that as well, though. If we know that we have your positional graph, because height being that position, we have negative 16t squared plus 64t. We know that the ground has a height of 0 feet. That's the ground. We can set it equal to 0, right? Again, them being the exact same. We have 0 is equal to negative 16t squared plus 64t. Let's go ahead and factor just like we did over here. So we can take out a negative 16. We could also take out a t. So it leaves behind a t that's positive, and then minus a 4. We can set them equal to 0. Negative 16t gets set equal to 0 this time because we took out a GCF of t. This one, because they didn't all have a t, notice that this one is missing a t. We didn't take it out. So here we do. We set them both equal to 0. So t is equal to 0 and t is equal to 4. The 0 is talking about this time right here, whereas this one is now the 4. So that is the math behind how we can use factoring to our advantage. The other way is if we know where your peak is, where your maximum or your minimum value, when we talk about your symmetry, if we go 2 units to the left, we can also do the same height 2 units to the right. Same thing over here. We went 1 to the right and 1 to the left. They'll achieve the exact same height. And when it says, what velocity will we hit with? We want to know how fast will it strike the ground. So we get your velocity equation, which was negative 32t plus 64. And we want to know what, at 4 seconds, how fast will it hit the ground? So we can go v of 4 is equal to negative 32 times that 4 plus 64. So how fast are we going to be hitting? So 32 times 4, that is negative 128 plus 64. We're at negative 64 feet per second. And again, the negative is talking about your height that is falling, not so much that the speed is negative. It's just referring to a negative height.